controllers. Sliding mode controller. All the controllers which you are going to study in this course are very powerful controllers. Even our students are also doing the same thing nowadays, SMC. Okay? I will come to the concept here, why you are using it. In practice, just let's read it now, then we'll go. In practice, the models used for model-based controller design will be imprecise. There will be some error in the modeling. This may arise from unknown external disturbance, unknown plant parameters, and parasitic model dynamics. Design of a controller which provides the desired performance of the closed-loop system in the presence of these disturbances is a challenging task. Right? Models will have some uncertainty, always, right? So the question is, we have to design a controller which should work, even if there is some uncertainty, which because uncertainty you cannot avoid it. There are so many possibilities. What are the possibilities? Robust control. Robust control, it assumes the amount of disturbance bound. If the disturbance bound is given, then it can perform fine, absolutely fine, robust control. Adaptive control is one of them. Robust control, always remember, there is another misconception. There is nothing like robust control. Always remember these things. There is nothing like robust control. A controller which has got the robust properties is a robust control. Up to what degree that robustness is there, that depends, will define, right? So, robust control, there is nothing like robust control. Although we say roughly that this is the robust control design, mixed sensitivity design, mixed integer programming design, that's fine. But essentially, there is nothing like robust control. We have to see whether that control is robust or not. Sliding mode controller is one of the robust controller. What is that? I'll explain these things here. Very powerful controller, no doubt. Just I'm reading the slides now, then we'll see. The sliding mode controller is a robust nonlinear control technique that forces a system state to reach and remain on a predefined surface called the sliding surface using a discontinuous control law. There are so many things I'm telling here. Many things are there in this slide. This controller is a robust controller. That means it has got some robust property. It is a nonlinear control technique. The control law is not linear. U is equal to minus kx is a linear. Is not linear. It is nonlinear law. Its system state to reach and remain on the predefined surface. You cannot understand. I will give an analogy shortly. Then things will be clear. Why it is not coming? Why not writing? Yes. Using a discontinuous control law. Let us understand the concept of sliding mode control nicely with an analogy, then only mathematics will follow. All of you, few minutes before, were in the corridor, right? Creating sound, noise. All of you, including me, right? Then Professor Rahul Kaur, what he thought, that these people are bloody idiots. As long as they will remain in the corridor, as long as they will remain in the corridor, they will create noise. Let us do one thing. push these idiots into this room. Push these people, you see, that's exactly what we are going to do. Not in the corridor, push these people into this room, and he knows the moment we are in this room, we cannot go anywhere. Clear? This is exactly sliding motor controller. This is exactly sliding motor controller. He knows because this is the sliding surface. So you have to push it by a control law here. Right? So because he knows, not only that, you see how it becomes robust. Mathematically, we can prove it. Once you are here, nothing can happen to you because all protection has been taken care of. Okay, if you are outside, then nobody takes care of you. That's the point. You have heard the story of Duryodhana. After the end of the Mahabharata war, not exactly end, when Duryodhana was not killed, he went to the Brahma Sarovar. Brahma Sarovar is the sliding surface. Because as long as he is there, nothing can disturb, neither the Lord Sri Krishna also. It's very difficult. That is the robustness. Once it is there, he there in the mother's lap, no force in the entire universe can disturb him. Lord Sri Krishna knew it. He is in the sliding surface. He is there. So to kill him, he has to be pulled from the sliding surface and applied it here. Kill him. Got my point? So the question is, you see, by hook or by crook, so suppose there is a child. He is moving here and there. By hook and by crook, if the child enters into the mother's lap, it is difficult. Your job is, if you want to make the child safe, you push him to the mother's lap. When the child is in the mother's lap, it is very difficult to take him out. Got my point? Exactly the same thing here. Sliding motor controller is like this. When V.I. Utkin found out this sliding motor controller, God given him this particular thing, he told that there exist certain places, if we just put him there, then no matter what happens, nothing can happen. Okay? You understand the concept here? So, sliding motor controller, now suppose, first thing is you decide what you want to do about the system. Suppose like 2 examples I'm giving. I know that if you will enter into a good restaurant, you will drink alcohol, you will make merry, then you are happy. I know it. Suppose my objective is you should be happy by drinking alcohol. Okay? So what I will do? I will make a control law who will put you into that hotel. Now suppose I want, instead of drinking alcohol, you should go to a spiritual function where there is a great sadhu is giving a discourse. That's my objective. So then what I will do? I will also push you, not to the restaurant, but I will to that particular congregation. Got my point? So you decide, first you decide where you want to put the people. System should be sliding where? First, this design of the sliding surface. First you design the sliding surface, where you should go. Got my point? That is called designing of the sliding surface. Whether you will come to the restaurant, you will go to a film hall, you will go to the beach. Okay, first you decide. Okay, design of the sliding surface. Then once I decide that I will put you people there, then I have to find out a vehicle. You are here. I want that you should go to the beach, dance it. So I must make some arrangement that you should go there. Otherwise, how can you go from this place? Right? So there is a reaching phase. You see, sliding surface is there in that mountain. There I want you to put. So then I will make a control law which will push you from this place and go there. And once you go there, I close everything. You are there. Nothing. Now, then you cannot come. Now you cannot come. So design the sliding surface. First point is design the sliding surface. Then find out a reaching law, a control law, which will make you to reach there. To reach there. And once you reach there, in the sliding surface, you are robust. Understand the concept? Sliding surface design, reaching law. I decide to put you in Mars. I decided, that is my objective. I'm getting money from GAM, good hotels, staying, getting good food, nice treatment here. So I decide I'm very happy, I will want to put you in Mars. Can I put you in Mars? Can I design a, so note that always the reaching law exists. You can, surface is Mars, but for that reaching law, reaching condition has to be satisfied. You should be able to reach there. You should be able to reach there. Not that always it is possible. Otherwise, anybody can put the system in any place, right? So design a sliding surface. Find out that it is possible to find a control law which can drive the system to reach there. That is not possible for all cases, just like I told you. It's not possible to put you in the Mars, right? Then system becomes robust, right? Yeah, sliding surface. Yeah. Yeah, sliding surface, yeah. But sliding surface is up to you. That's the design criteria. Whether it will reach there or not, that depends on the system condition. There are conditions. Got a point? Sliding surface, you can design. But whether you can reach there or not, that depends there. Okay. Step 1, design the sliding surface. Where you will put it, right? Whether in the beach or in the hotels or in the cinema hall, what is the sliding surface? Because where you will slide, okay. Design the sliding surface, sigma x is equal to x is the state variable. Define the sliding surface that the system trajectory will reach and stay on. This surface serves the desired closed loop dynamics. Right? What you want, that will be there. Now, the dynamics on the sliding surface should be asymptotically stable, okay? And it should be reachable. Just like I told Mars, you cannot reach. Mars, you cannot reach, okay? So the system must be stable in the sliding surface. This is the condition. And that's the reachability. You should reach there. Just to change this thing. So why? Okay, that's reachable. You should be able to reach there, right? Suppose you will say, I want to my sliding surface in your sun. You are not Lord Hanuman that you can reach there. Is not reachable. So reachable condition is not satisfied, right? It must be possible to bring the system from any initial condition to this surface in finite time using a control law. That is a finite time condition of reachability. You say it is reachable. Auckland is reachable from Goa. Yes, it is reachable. Reachable, you will reach it by walking. You made a control law by walking, so you will reach after 20 years. Got a point? So we should define a sliding surface. It must be reachable in finite time. Because if it will reach after last time, there is no meaning, right? So these are the conditions. Stability, it should be stable, it should be reachable. Because remember, once you are in a sliding surface, all problems over. The modeling uncertainty, everything, system will be robust. No input constants. I understand what you say. No input constants, no. No input constants. That's a good thing, yeah. Once the sliding surface is defined, the next task is to design a variable structure controller that ensures all system trajectories reach the sliding surface in finite time. Once on the surface, the system remains confined to it. That we have to see. The variable structure controller is a sliding mode controller is a subset of the variable structure controller. Because I am coming to that point, variable structure controller. Sliding mode controller is also a variable structure controller, but variable structure controller is not necessarily a sliding mode controller. Structure of the controller is variable. I'll explain you what is that. I'll give you an. Have you seen the young people or the elder people playing with the children? Suppose you hide and seek, or you are here, and you ask a child, you catch hold of me. Now see here. So what you did, you move. The child is the controller, or you are the controller, so the child is following you. Now suddenly you make a change. The moment you suddenly make the change, there is no finite trajectory. There is no finite trajectory. He doesn't know which trajectory he will take. Otherwise, he can design a simple controller so that he can follow you. He doesn't know what the finite trajectory. So what he will do, depending on how you change, he will change. Right? So similarly, if you change the control law, then what happens, the system behavior sometimes is oscillatory, sometimes damped oscillatory. You see, depending on the control law. No, this is not coming out the sliding surface. This is the control how you are going there. Yeah, yes. Sliding surface. Yeah. You have PI controller. Yes, PI controller. Yes. Each structure go on changing. Yes, that's the point. The problem is, see the analogy will explain, otherwise mathematics is simple. You design the sliding surface. The theorem says if you are in a sliding surface, you are safe. You are safe, okay. So I know that if you are coming to this room, you are safe. So you are in the hostel. I know that you are coming to this place, you are safe. So I am making a control law which will bringing from the hostel to this place. The problem is, you must come from the hostel to this place. In between, there is no guarantee what will happen. So the reaching phase should be as quick as possible. Because in the reaching phase, there might be some problem. We cannot ensure anything. Suppose you are coming to a hostel, you are safe here. But while coming by bus, you don't know whether the bus will break down or something. That guarantee I cannot take. In the reaching phase, when the system is coming from that initial state to the sliding surface, no guarantee. So we say finite time convergence to the sliding surface, finite time, and that time should be as quick as possible. Because no robustness, nothing. Nothing is guaranteed. Nothing is guaranteed. Just like insurance policy. If you do the insurance policy from tomorrow, insurance will take care. But from today until tomorrow, insurance is not going to take. Which insurance says that your insurance is from tomorrow. If you are in a sliding surface, I will take care. How to come to the sliding surface, that is your job. Got my point? No. No, yeah, that we are coming to that. No, that is depends, but always reaching condition not satisfied. That you can design any sliding law, sigma x is equal to 0. The reaching condition says sigma x into sigma dot x should be less than 0. And sigma dot x depends on the system dynamics. You may not reach there. The control input in the sliding mode controller essentially consists of two things. One is called the equivalent controller. Another is a nonlinear controller. Okay? What is that? I'll tell you like this. This is the sliding surface. This room is the sliding surface, right? You are outside. Now I am pushing you to come to this surface, right? But usually, just like human beings, the system states will not always remain here. I am asking you, say the very common thing, I will ask you all, go to your place, go to your place, go to your place, right? Now, somebody is standing on the door, and he will be looking whether you are in the room or you are outside the room. Usually, for some people here, they will not be here. They will try to go out of this. The moment they try to go out, that fellow standing there will push him. That is the nonlinear control law, this component. That's a switching law. If you go that side, it will push it. The two people, I will put it. That door, two doors are there. If this is the sliding surface, so this controller will push you here. If you will always do oscillate here, because you are this is the nonlinear controller will always push you. You go here. The nonlinear controller. Okay, so that particular switching law component is this one. And when you are here, the controller which is there, that is equivalent. Yes. No, not always. Yes. Yeah. That's right. Yeah. The two components, one is equivalent control, keeps the system trajectory on the sliding surface once it has reached it, derived by forcing sigma dot x is equal to 0 under ideal sliding conditions, represents the continuous part of the control, this one. This nonlinear part drives the trajectory towards the sliding surface. So if you are just outside, little bit outside, it will push it. It drives. From any initial condition, typically discontinuous and uses sign of the switching function. Right. What I want to say here, another thing. Any switching function, anything where you do the switching, there will be switching harmonics, switching transients. Okay? So the system becomes maybe a linear system, but due to switching it becomes nonlinear. Right? And when it becomes nonlinear, you do not know what sort of frequency it will generate. Right? One point I forgot to tell you at the beginning, in the morning lecture, in signal processing, in filtering, we have been taught if there is a noise signal, you design a filter, it will filter it out. That's clear. Obviously, no problem. If the signal bandwidth and the noise bandwidth, they are separate, then you can use a filter. Signal bandwidth and noise bandwidth. But if they overlap, then by filtering the noise, then also filter the signal which is not desirable, right? So these type of things, normally what we do in power electronics, those people who are working in power electronics, they know. We have been taught a signal f of t can be approximated by a Fourier spectrum consisting of sines and cosines, right? And there those components are superharmonics. We say superharmonics. F of t is called f0, this component, sin omega t, sin 2 omega t, sin 3 omega t, sin superharmonics. Nonlinear systems can generate subharmonics. If it is superharmonics, that's fine. You can use a easy filter. If the subharmonics, the techniques are there, no doubt. Professor Vida Kumar knows it. The filtering techniques, they are the experts on that. I'm not saying that it's not possible, but you must be careful whether it is superharmonic or subharmonic. There might be some intermodulation. Suppose your system is excited by omega 1 and omega 2, the generation frequency omega 1 plus omega 2, omega 1 minus omega 2, omega 1 plus minus 2 omega 2, omega 1 plus minus minus. You see, there are many complex frequencies will generate it. And the switching functions are the useless functions actually. You know what the switching functions? Switching people are always idiots. You know it or not? The way human beings behave, the system behaves exactly in a similar way. Today in this party, switching the another party. The next party, you know, switching. They are the useless people, right? So switching functions are dangerous things. Got a point? So sliding mode concept is clear. Is there any problem? First design a sliding surface, then see that it is possible to reach there. Reaching is the first thing. Before designing any control law, first see, design a sliding surface and see whether it is possible to reach there or not. Now, if it is possible to reach there, then you find out a control law. Right? The control law has got two components. First component is, once you reach here, inside this room, then there must be some facility, there must be a chair, there must be a table to sit here. Okay? That is the equivalent control law. This part will decide. And there will be some people, they are not used to be in this room, so I will keep those two people outside. So the moment you just go a little bit outside, they will push you. Be here. Right? The theory says, it is there, I am not proving it here. The theory says sliding mode is robust against matched uncertainty. This point I will explain you. Matched uncertainty, very carefully understand what the matched uncertainty. Not any sort of uncertainty. Matched uncertainty. What is matched uncertainty? Or matched disturbance. You can say matched disturbance, let's say. If the system is x stat is equal to linear system, let us say x plus bu. X stat is equal to x plus bu, right? What is x stat is equal to x plus bu? What is the meaning of that? X is the internal variables. BU, you see here, this is the room. We are all state variables. That door is the B channel. That is through that the input signal comes. Got a point? The input signal comes from where? From that door. That is the B matrix. U comes through B. Through that particular door comes. Now, this particular thing, all the input signal comes to that door. Suppose the system is disturbed. Suppose the system is disturbed. That is the input. That is the system states. And that is a disturbance. That is a disturbance. Say X dot is equal to AX plus BU plus E into D. E into D. That disturbance is called a matched disturbance. Matched disturbance. If that disturbance also enters in by that door using the same path. If the disturbance comes from other side, sliding mode controller cannot work. System, it is robust against system disturbance, which is not exactly system disturbance, matched disturbance. That means your input comes in that door, just like suppose you have got a house, 3 doors are there, right? You come through one door, so any idiots who are coming through the front door, you can take care of that. If somebody is coming from other side, you cannot take care. Clear? Matched disturbance and unmatched disturbance. Matched disturbance means the same door where the input is coming, the disturbance, assuming that disturbance is also coming through the same door. But disturbance can come from other doors also. Got a point? You understand any doubt about matched uncertainty? Matched uncertainty means the analogy is clear. The door is the B matrix. The input is coming in that door. The during the no reaching phase nothing no. Yeah? No, all uncertainty should be matched uncertainty. All uncertainty should be matched on uncertainty. A plus delta A, X, so it will take care. That's all proof is there in the lecture handouts. Right? Any questions here? Because I'm not going to enter, there's some, today, what is that? Handouts in the assignment, I don't know what is there in today's assignment, but any questions? Understand the concept clear? Sliding mode controller, what it does. Okay, once you sliding mode, so one thing in the nonlinear system, I forgot to tell you during that time that superharmonic, subharmonic oscillations, intermodulations, okay, those things are always present. Always present. One interesting thing I'll tell you, and I'll close the lecture today. I think people who are teaching signal processing must be knowing that. On the frequency component, any function we are approximating usually at the beginning in the school level by Taylor series approximation. Have you seen it? A function f of t around a particular point can be approximated. See here, I'm writing it. Correct me if my expression is f of x at x is equal to x0 is equal to fx0 plus del f over del x at x is equal to x0 into x minus x0, right? Something like that. Other things I don't remember it, so it's a Taylor series expansion. Higher order terms, right? Taylor series approximation. This will help you in teaching the students actually, what I'm saying. This approximation, we are using it and it has been used for many years. Month of December, very cold time in Paris. There is a guy who is not a mathematician. There is a person who is not a mathematician. He is an engineer, the son of a Christian parish. His father is a priest in some of the church. There is a mathematical conference where mathematicians were there, students of Laplace, Poisson, Leibniz, his students. Understand the scenario? I am telling you, for the academics, you have to explain to the students to make the things interesting. He told, first thing, those people who are mathematicians, they don't want to listen to this bloody fellow. He's an engineer. He knows nothing about mathematics. That is the view. He told, you see, you are telling me that a function f of t, you can approximate the function by a series. I have got another function. Okay? It can approximate a wider range of functions than the Taylor series. Then people asked, what? You are proposing a method which can approximate. He told that the Taylor series which you are using for approximating cannot approximate a discontinuous function. But my proposal is it can approximate anything. There are some people who are students of Taylor also, subsequent students. They shouted, your knowledge on mathematics is big zero. Don't talk nonsense here. He told, I can show you now. I can tell you that any function in this entire cosmos can be approximated by a simple continuous time function, sines and cosines. Just powerful statement. Powerful statement in the month of December in Paris conference, mathematical conference. I have got a function which consists of only continuous time functions. It can approximate both continuous time function as well as discontinuous functions, and my series is nothing but sines and cosines. Again shout. How can continuous time functions added together can approximate a discontinuous function? That's the point. Right? And that is the series. That fellow is Jacques Fourier. Fourier series. He told any function in this cosmos can be approximated by sines and cosines. And he told one of the powerful method of his method is, see how it is coming from. He told that you are using a differentiation operator in the approximating. Del f over del x. And differentiation operator, I told you, division operation is a useless operation, right? He told, I don't use any differentiation, I use only integration. You cannot divide it because there is a possibility of division by zero. But addition by zero, what is that? You see, Fourier series, everything is integration. Right? When Jacques Fourier told these things in the mathematical conference in Paris, with lots of objection, people said it took around 50 years' time to see that what Jacques Fourier told, that is correct. You got my point? So for teaching to the students, you can tell them this story, that how this Fourier series came into picture. A function can be approximated by sines and cosines, a continuous time thing. Okay. I will close it now. Okay. Our boss is telling me, no doubt. No. Example will be there. Example is there, no doubt about it. I'm just, yeah. No, absolutely fine. This is the proof I'm giving. This is the proof given. Example is last. Robustness proof. Example is here. X dot is equal to X plus BU plus DT. System is disturbance. Let us define the switching surface sigma x is equal to X. Now, you want a control law. It has got two parts. One is the equivalent, you see, ut is equal to one linear part and one nonlinear part. The linear part will ensure that system is in the sliding surface, and that is computed by making this dt is equal to 0. Now, if I make dt is equal to 0, x plus bu is equal to 0. So, u is equal to minus b by minus a by b into x. Clear? So, this is the part u equivalent is equal to minus a by bx. First part. This is the control law which will keep the system in the sliding surface. But if the variables go out of the sliding surface, somebody should be there to push them. That is the nonlinear control law. Nonlinear control law which will push it, it is not standardized. There are many types of nonlinear control law which are there. Usually a sign function. Sign function means if x is greater than 0, push it here. If it goes this side, push it this side. If it comes this side, push it this side. Right? So therefore, you see this is the equivalent part and this is the system is this. Right? You will do an example here. Have I given the example in the program? Or I think I have given that. Yeah, yes. Similarly here, you see. But that's the problem with the sliding mode controller. Because of the switching law, the response will chatter a little bit there. But that's fine. There are thousands of papers, chattering reduction, reduce the chattering, how this is reduced, so those things are there. But the important point is, it is robust. It is robust whenever in the sliding surface. That point you have to be very careful. It is not robust when you are traveling from a hostel to this room. No. There somebody can kidnap you. You don't know. So reaching phase should be as small as possible. The reaching phase should be as quick as possible. Because by that time there is no guarantee. Guarantee will be taken whenever you are in the sliding surface. Okay? Any questions? No? Yeah.
So what is the chattering in sliding mode control?
Chattering means because the control law, because the nonlinear control law, see, that's the point. Again, the same analogy. You should understand the concept, always think of the analogy. You are in this surface. Some people, chattering will come because of the nonlinear part of the control law, right? So that is one person who wants to go out of the room. So the control law, what will do? He will push him. In normal case, what you will see? He wants to go out. Then you will push him. Then he will shout or he will not shout. He will know why you are pushing me. Same system also tells the same thing. It will chatter. What about? I have studied the control theory. What humans behave, the systems behave exactly the same thing. The moment you push him, then You give a large controller port, it will shout more. Hey, why you are doing like this? So the amplitude will go up. Okay, so chattering. The wording is not something. There will be chatter, there will be discussion, because the person is standing there, he's trying to go out, he's trying to push him, so there will be dialogue. Yeah. Any? No, I have never done it. Because always we say that try to use those very simple controllers. I am against using very complex controllers. Because nowadays all these people are doing it. Sliding mode, MPC, PID, observer, all four combined together. Our people are doing it. Our people are doing it, I am telling you. I am doing it. I am doing it. Yeah. Yeah. Yeah, slide is supposed to be stable, yeah. Yeah, it will work. It has no assumption. No. Very simple. You see, the only thing that is the reaching law should be there. Plant is unstable. I am violent, but I am by the reaching condition is satisfied. Suppose I am violent, I am unstable, but the condition says that the sigma dot is less than 0. That means it is possible to reach here. So you are unstable, but you are creating disturbance, but doesn't matter. I have put you in the boss, you are coming here. You may be unstable, but you are reachable. You got a point. You are unstable, but you are reachable. You are disturbance maker, but I can take you to Mira beach. You are not, if you are a good person, that's fine. But you are a bad person, but I have got a capability. You also agree to go with the Mira beach. So I am taking you reaching phase. Reaching condition has to be satisfied. That is important. No, reaching phase has to be calculated before. Sigma dot is less than 0. I think the proof is there somewhere. One minute. I think. Sigma x is equal to x. Sigma x is equal to x. So sigma dot x dot is less than 0. That condition only is satisfied, it will not happen. Any other questions? I couldn't get it. That. It will change it because it will now behave as per the sliding surface design. No, the theory is for nonlinear system only. You see here, I can see here, this is the linear system we have defined here. So, suppose x dot is equal to x plus b is linear system, and this is the disturbance, and this disturbance you are taking sine wave. You are saying this disturbance is sine wave. No, I don't know, I understand that, what you say coming. Sliding mode controller has to be designed. It is not a model-free controller. It is not a model-free controller. The system has to be represented by a model, either a linear model or a non-linear model. This example here, you know that I think the assignment that the non-linear model is there or something like that. So what you are telling that the signal, have you model it as a XT or something like that? Is it in this form? This form. So what the sine wave is there? Where? In the x is equal to ax plus bu, what is the sine wave? Ax is sine wave? Ax is a sine wave. I couldn't understand how Ax is a sine wave. What is the system matrix? Yeah. Yeah, you represent that thing in the state space. Then only you can apply these things. So have you modeled that inverter in the state space? What is that A matrix? Yeah. Yes, that's the point. No, U of t is a noise. Huh? No, that means BU, not BU, that is, sorry. Like that. Yeah. So BU is the noise. So that your system doesn't have an input. X dot is equal to AX plus noise. Huh. 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 Oh, okay. So, so what you do in that case, I understand what I was saying. So now, you keep something BU because input has to be given. That noise which is coming, that will be represented as D zeta. Huh? No, there is no point in removing it. And also, there is no need of knowing the D also. There is no need of knowing the D. You can still design it automatically, this will filter out, sliding mode control. That is the theory. Even if there is no need of D to be known, you take the system, but you have to apply this U somewhere. You are saying that U is not there. That's you. Without U, how can do it? Yeah, U is there. Uh-huh. No, see, you are saying that this U is changing the, we will talk offline, we'll see. I'll see.